fares $20.99. A train hurtles through a tunnel at a blinding speed, 5,000 miles an hour, on a journey through the Atlantic Ocean. Its passengers just had dinner in New York, and in less than an hour, they'll be having dessert in Paris. Science fiction? Perhaps not. A transatlantic tunnel may be closer to reality than we think. But just how would such a staggering project ever be built? Even if it could be completed, could it withstand the horrific dangers that would surely confront it? And if it is successful, could it provide the model for other tunnels that would one day link the people of the world across the 7 seas? Planet Earth. 70% of the Earth's surface is water. From time immemorial, the oceans and seas have been a mighty barrier, separating the peoples of the world. Over time, transoceanic travel has been mastered, but it is still not without difficulties. In the not-too-distant future, there may be a radical new way to cross the oceans, one that will forever transform life as we know it. More than 3,000 miles of ocean separate the old world from the new. A transatlantic tunnel would be the most massive construction project in human history, requiring global resources on a scale never before imagined. $1 billion tons of steel, the combined output of all the world's steel mills for an entire year. Over 50,000 tunnel sections, each weighing thousands of tons. Securing each to the ocean floor. The cost would be staggering, $12 trillion, and would take a century or more to complete, under some of the most extreme working conditions on the planet. But if completed, the transatlantic tunnel would change people's lives like nothing before. 60 million people cross the Atlantic every year. Most fly. And still it takes the better part of a day. A transatlantic tunnel would shrink that trip to less than an hour. One could easily live on one side and work on the other. An impossible dream? Frank Davidson doesn't think so.
Transatlantic tunnel is not beyond the reach of modern science and technology. It's a matter of getting used to new realities.
And Davidson should know. His firm helped design the English Channel Tunnel, linking England and France. The tunnel was also considered an impossible idea. And yet today, 6 million passengers a year make the 3-hour trip between Paris and London. But at 31 miles long, the tunnel seems little more than a short hop compared to a 3,100-mile-long transatlantic tunnel. The idea of a transatlantic tunnel has inspired visionaries for over a century. In 1895, Jules Verne predicted carriages traveling at 1,000 miles per hour, propelled through a tunnel by huge steam-driven fans at either end. In 1972, science fiction writer Harry Harrison envisioned a transatlantic tunnel partially supported by vast undersea bridges. Lately, engineers from Switzerland, Japan, and the US have proposed networks of underground tunnels to move freight below traffic-clogged cities. But constructing an underwater tunnel to carry passengers across the Atlantic would pose challenges of unimaginable proportions.
There are many factors that make it an extremely difficult, if not almost impossible project. The very limited weather windows for construction, the extreme distances that you'd have to move materials, and of course, the cost of this enormous project.
Difficult, dangerous, astronomically expensive, and in the minds of some visionaries, altogether possible.
When you start looking at the problems systematically, they will yield to research and development.
The first critical step would be mapping out the most practical route. Since undersea construction can run as much as $4 billion a mile, the cheapest path would be the shortest one. An early proposal took the northern route, beginning at the edge of Canada's Newfoundland coast, then dipping in and out of the ocean, over Greenland and Iceland, before splitting toward Scotland and Norway. Compared to a completely submerged tunnel from New York to England, this route would cut underwater construction in half. But the problem is the overland portion. The extreme weather conditions during Greenland winters are all but certain to slow traffic due to ice and high winds. The best route may also turn out to be the most expensive. A straight shot 3,100 miles underwater from New York City to the coast of England, and on to London and Paris. But could it really be built? The classic way to build a tunnel is to dig. That's how the channel was made. In 1987, workers on the French and English coasts launched two huge drilling machines aimed directly at one another, each boring a hole 25 feet in diameter, 150 feet below the channel floor. Three years later, the two teams met up at the midpoint, and the drilling was complete. But could engineers drill a tunnel under the ocean floor, all the way across the Atlantic? Unlikely. The tunnel took 3 years. At that rate, a transatlantic tunnel would take more than 3 centuries. And there's another problem. The channel lies only 300 feet below sea level. A transatlantic tunnel would in places sink almost 5 miles below the surface. The pressure at that depth, almost 500 times greater than at the surface, is simply not survivable. And it gets worse. The Mid-Atlantic Ridge, a volcanic undersea mountain range, would be directly in the tunnel's path. The area averages a remarkable 5 earthquakes every day. Drilling in such a seismically active area would be foolhardy at best, deadly at worst. So drilling under the Atlantic Ocean floor won't work. But what if a tunnel could be fabricated in smaller segments on land, then linked together along the ocean floor? This design, known as an immersed tunnel, has been in use for more than a century. The world's longest immersed tunnel was built here in the city of San Francisco in the 1970s. Every day, that city's famous subway, known as BART, takes thousands of commuters across the bay through the world's longest and deepest immersed tunnel. It extends for more than 3.5 miles, sitting 130 feet below the surface, along the bottom of the bay. The tunnel is composed of 57 prefabricated sections, each 24 feet high and 330 feet long. Immersed tunnels have proven safer to build than tunnels bored through the earth. Could an immersed tunnel 1,000 times longer than San Francisco's cross the floor of the Atlantic Ocean? If so, construction might begin here in Holland, at one of the world's largest tunnel factories. With nearly half the country below sea level, the Dutch build more immersed tunnels per square mile than any other nation on Earth.
Imagine you have a large tunnel. It could be a tube or a box-type tunnel. You cut it in pieces. But first you have to build those pieces.
Building an immersed tunnel begins with concrete. Lots of concrete. First, a concrete floor is poured onto a giant preset form. Once the floor dries, the walls and roof can be poured. Each 300-foot-long section of tunnel consumes almost 30,000 tons of steel and concrete. Enough to build a 10-story apartment building. If the concrete dries too quickly, it will become brittle and possibly crack. That's why workers continuously run giant steam generators over the concrete for up to 28 days. When finished, each tunnel section is about the length of a football field. A transatlantic tunnel would require 54,000 prefabricated sections, which would take 225 factories, each working around the clock, 20 years to produce. Of course, building the tunnel sections is only the first step. Then they have to be moved out to sea and pieced together like a huge Lego project. First, each section is sealed tight with steel bulkheads at each end. That makes the sections watertight, so they actually float. Next, the dry dock is flooded, and these massive tubes can be simply towed out to sea.
We can actually float each element out of this dry dock automatically whenever we want.
If these sections were destined for the transatlantic tunnel, they'd be on a very long journey. Sometimes as far as 1,500 miles. This final stage of the process is by far the most difficult and dangerous. And the work must be performed far beneath the surface. Each section is carried to a point directly above its final underwater position by a specialized ship called an immersion pontoon. It is then partially flooded, causing it to sink. Robotic winches control its descent. A team of divers working in near total darkness relies on global positioning systems to maneuver tunnel sections to exactly the right spot. The work is very dangerous. If a diver found himself in the wrong place at the wrong time, his air hose could get pinched by a tunnel section and he could suffocate to death. Final placement is critical. Each joint must be lined up precisely on both ends. Huge rubber gaskets are used to form a perfect seal. Immersed tunnels sit in a carved trench to provide a snug fit to the bottom. Once the sections are in place, the bulkhead seals are cut away and the watertight tunnel is complete. This process has been perfected for building underwater tunnels in rivers, bays, and other small bodies of water. But could it be adapted for a transatlantic tunnel? Unlikely. The Atlantic is simply too deep. At just 1 mile down, water pressure is 165 times greater than at sea level. In the deepest ocean, 800 times greater, nearly 12 million pounds of pressure per square inch.
Ordinary tunnel sections would just be crushed to dust in that sort of pressure, which amounts to something like a 747 sitting on a square foot of the tunnel, on every square foot.
There is, however, another kind of tunnel that doesn't lie on the ocean floor. It is an idea that is so new, it has never in fact been tried. But some engineers think this radical design might provide the breakthrough necessary to build the Transatlantic Tunnel. And it could all happen here, in Norway. This area along the coast is one of the dozens of deep inlets carved by glaciers thousands of years ago. It's an area of Norway characterized by a sweeping natural beauty that more and more attracts a horde of tourists, causing constant traffic nightmares. Car lines for the ferry snake back for hours. The only alternative is to have your own boat, or risk a treacherous drive around the mountains that can take hours. There are no easy solutions to the problem. The fjord is too deep for a standard immersed tunnel. And local leaders fear that a bridge would be an eyesore. It seemed an impossible situation. Until 1987, when a group of private engineers were ready to test a bold new theory. A tunnel that actually floated, submerged at about 100 feet below the surface. A submerged floating tunnel.
The submerged floating tunnel and the immersed tunnel are very similar, but the immersed tunnel is resting in a trench on the bottom of the crossing. The submerged floating tunnel is suspended in water and has water all around it.
The design is ingenious. Inside the tunnel, a carefully controlled balance of air and ballast enables it to float at a precise depth, in this case 85 feet below the surface. The technique is already in use today all over the world, in submarines. Inside a sub, ballast tanks, sealed off from the living quarters, can be alternately filled with water or air, changing the sub's weight and its buoyancy. The submerged floating tunnel would work the same way. But to make sure it doesn't pop to the surface, a series of tethers would anchor it to the bottom. If built here in Norway, a submerged floating tunnel would solve the traffic problem while preserving the region's natural beauty.
When you look at all the alternatives, the submerged floating tunnel becomes very interesting very quickly.
But like all revolutionary ideas, the submerged floating tunnel has run into public skepticism. Nobody, not even here in Norway, wants to be the first to commission the new tunnel design. The local government has postponed the project. But the engineers remain optimistic. They're convinced the technology will prove itself once given the chance. And what about in the Atlantic? Could a 3,000-mile tunnel actually float between New York and the United Kingdom? Walter Grants has worked with floating tunnel designs, and even he's a skeptic.
It would be a very impressive structure if you could see it underwater, running all the way from London to New York.
The critical problem, how to keep it in place. What would prevent such a long floating tunnel from, well, floating away? In some locations, it might be possible to build giant piers, like an underwater bridge. But not in the Atlantic. It would take thousands and thousands of towers, many of them miles high, hundreds of times higher than bridge piers anywhere. The piers themselves would be a larger construction project than the tunnel. Another option would be to support the tunnel from above. Huge floating pontoons might hold the tunnel in place from the surface. Just not here, where the pontoons would be subject to the violent weather conditions in the Atlantic. Worse yet, the Atlantic is home to the powerful Gulf Stream. Currents constantly moving 100 times as much water a day as the Nile, the Colorado, the Amazon, the Mississippi, and the Yangtze rivers combined. But there is another technology for supporting massively heavy floating objects at sea. And it's already in use. In offshore oil platforms. 100 miles off the coast of Norway in the North Sea, the Hydron oil platform sits smack in the middle of the Gulf Stream's forceful currents. It stayed in place for almost a decade. In the early 90s, the platform was built in a shipyard and floated whole out to sea. Earlier oil platforms had used solid concrete piers to keep them in place. Once finished, they couldn't be moved. So engineers decided to try a never-before-tested technique. To the underside of the platform, they attached 1,000-foot-long steel pipes, just long enough to reach the bottom, where powerful suction anchors were driven into the sea floor. As the anchors were driven in, water was sucked out, creating a vacuum seal. The anchors had to be strong enough to hold the 360,000-ton platform in place. and the platform can still be easily moved to a new location, simply by pulling up the anchors. The system relies on the same scientific principle as a pendulum, only upside down.
If you remember a grandfather clock, when the weight is up here, it is forced down by gravity. If you just reverse that and put a buoyant element on the top and anchor it to the Z bottom, when the waves then come, it is pressed a little bit down into the water and buoyancy presses it up.
Since the hydrant platform proved that the technology worked, the technique has been adapted for other platforms, as well as for proposed floating tunnels. But could it be adapted to the Transatlantic Tunnel? Engineers believe the ideal depth for the tunnel would be about 150 feet. That's deep enough to avoid ship traffic, yet shallow enough to minimize pressure problems. Steel cable tethers, like the kind used in suspension bridges, would hold the tunnel in place. But with one important difference. The cables on a suspension bridge keep the roadbed up. The cables on the tunnel would be holding it down. They'd provide not only the strength to hold the tunnel in place, but also the tiniest degree of give. The tunnel would need to sway just a bit to absorb the energy of underwater currents, the inevitable collision with a large sea animal. Or perhaps even worse. So what is the most likely design for a transatlantic tunnel? Engineers now believe it would be built of 54,000 prefabricated individual sections. Each section would have an outer skin of stainless steel. Directly beneath the steel would be a layer of superbuoyant foam. Under the foam, another steel hull. And inside that, the tunnel's concrete interior. The interior would hold eastbound and westbound tracks, as well as a centrally located auxiliary track for emergencies. Above and below the tracks, service tubes would provide power, communications, and access for repair. And since the Atlantic is seismically active, the entire tunnel, along with its 100,000 tethering cables, would be monitored continuously by a massive geopositioning system. Any shift in the sea floor would trigger an automated system-wide retensioning of the cables. If ever built, the Transatlantic Tunnel would be the largest, most complex, most expensive construction project in history. It would take thousands of workers laboring for decades, under some of the most extreme conditions anywhere on the planet, especially out at sea, where specialized teams would sink, attach, and tether the massive tunnel sections, all 54,000 of them. The first sections might be attached under New York Harbor, and the work would then move out into the Atlantic. Workers would live on board floating platforms, which would keep moving out to sea. Divers would help maneuver the sections during placement operations. But attaching the tethers to the sea floor would most likely need to be done by submersibles, since no diver could survive the pressure at those extreme depths. Engineers estimate the tunnel would consume the entire output of every steel mill in the world, working 24 hours a day for more than 1 year. Which of course raises one more staggering problem.
The cost of the transatlantic tunnel would be in the trillions, perhaps the tens of trillions of dollars. In fact, the cost of the tunnel would be in excess of the gross national product of a large number of countries.
You would need combined operation of government and private industry and public sympathy, thinking more optimistically about improving the terms of life on Earth.
Even if it could be built, there's a larger question. Would it be worth the effort? Could such a vast undertaking ever justify its huge cost? The answers to those questions depend on one thing: speed. Unimaginable speed. Up until this century, the fastest way across the Atlantic was by ship. A one-way trip took about a week. Planes, and later jets, brought the trip down to hours. Today, the fastest way is the supersonic jet called the Concorde, which makes the trip in about 3 hours. But the Concorde is so expensive, only a few can afford to fly it. Could a train go faster than a supersonic jet? One thing is certain: there could be no diesel trains in the tunnel. There would be no way to vent the deadly exhaust. The only possibility would be an electric train. A very fast electric train. Today's fastest trains run between Tokyo and Hiroshima in Japan. They're known as the bullet trains. These sleek state-of-the-art trains will approach top speeds of 250 miles per hour. Not bad, but nowhere near fast enough. To make the Transatlantic Tunnel feasible, designers would need to build a train that went 20 times faster than today's fastest working trains. And as incredible as that seems, it's theoretically possible. The main limit to the speed of a train is friction, caused by their weight on the tracks. But what if that friction could be reduced or eliminated? Here in Germany, engineers are testing an experimental train that all but eliminates track friction. Because the train doesn't ride on tracks. This train literally floats on a magnetic field. It's called maglev, for magnetic levitation.
Maglev technology is doing what a typical train does, except using electromagnets. Instead of having wheels and rails, we have magnets to lift and guide the vehicle, and then a non-contact propulsion system to propel the vehicle down the track.
With a powerful enough magnet, literally anything on Earth will levitate. A drop of water, an ice cube, even a strawberry. Maglev trains work like this. When the system is first powered on, a powerful electromagnetic field lifts the train up, about an inch off the track. Powerful generators in the track then begin to produce waves of magnetic energy, which propel the train forward. Because the train never makes physical contact with the guideway, there's no friction. And that makes the train very fast. The current model is designed to go as fast as 310 miles per hour, but the technology can potentially go much faster.
In theory, there are no limits to how fast a maglev system can actually go. There are obviously practical limits. There are also economic limits. But the technology itself is capable of much higher speeds.
Maglev technology holds the greatest promise for a transatlantic train system that might someday hurtle through an undersea tunnel at the speed of a rocket. But in order to reach 5,000 miles per hour, another problem would have to be solved. The primary force that limits the speed of all moving objects: air resistance.
The faster you go, the more air resistance you have, which means the more power you use. And so if you can do away with that air resistance by putting the train in a vacuum, then obviously you could go at much higher speeds with the same amount of power that we're currently doing today for 200 miles an hour or 300 miles an hour.
The transatlantic tunnel would need to be totally airless. A perfect vacuum. Vacuum tubes are nothing new. The technology was developed a century ago to send documents and small parts through factories and offices. The concept is simple. Pumping all the air out of a tube creates a vacuum. With no air, there's no air resistance to any object going through it. Give the object a shove and it goes into the equivalent of instant freefall. It's literally sucked through the tube. Could engineers turn the transatlantic tunnel into a vacuum tube? Engineers at MIT are experimenting with a working scale model to find out. A miniature maglev train is placed in a tube that represents the transatlantic tunnel. Smoke is added to show the presence of air. The train slides slowly. Next, all the air is removed with a vacuum pump. Now, when the train is added, its speed is tripled. Without air to push it back, the train slides completely unimpeded through the tube. Of course, removing the air from a 6-foot tube is one thing. Turning a 3,000-mile-long train tunnel into a vacuum is quite another matter.
To initially pump all the air out of the transatlantic tunnel in order to create the vacuum necessary for high-speed travel, we require several months of pumping at millions and millions of cubic feet per hour of pumping speed.
It would take the pumping force of about 100 jumbo jet engines running continuously at full throttle for about 2 weeks. But even assuming the magnetic power and vacuum technology all fall into line, engineers would face another potentially crippling problem. The deadly force of acceleration. How could the human body tolerate the crushing G-forces that would almost certainly occur at those speeds? When an object, space shuttle, jet plane, or train accelerates or changes speeds, its occupants will experience either a sense of increased weight or a sense of lightness. These are G-forces. Shuttle astronauts can experience up to 3 Gs, or 3 times the normal pull of gravity, as the rocket accelerates from 0 to 17,000 miles an hour in about 8 minutes. Of course, once they reach orbit, they feel no G-forces at all. Even though they're traveling at 17,000 miles an hour, they are not accelerating, so there are no G-forces. This fighter pilot is undergoing 9 Gs during a simulated dive,
4 Gs,
making him feel like he weighs 1,500 pounds.
burnout 6 Gs,
The blood stops flowing to his brain, and he momentarily blacks out. If the transatlantic tunnel train accelerated at the rate of a space shuttle, the G-forces would turn it into a tunnel of torture. If the passengers aboard a transatlantic train had to endure those kinds of forces, there'd be plenty of seats available. Fortunately, that won't happen. The key to comfort would be a controlled, gradual acceleration. Beginning its journey east from New York City, the train would first pass through an airlock, accelerating gradually for the first 750 miles. Taking a full 18 minutes to reach its top cruising speed of 5,000 miles an hour. Passengers would sit in pivoting, rotating seats, designed to further reduce the G-force effect. And since the train literally floats on a magnetic field, passengers would detect almost no shaking or jolting. Each car would be the equivalent of a sealed spaceship with its own pressurized recirculating air. At top speed, the train would actually travel faster than a bullet fired from a gun, covering 1,600 miles in the next 18 minutes. The final leg of the journey would be an 18-minute deceleration. The train would pull into London Station exactly 54 minutes after leaving New York. Less time than an hour's ride to the airport in rush hour. Power for the system would come from generators located at the two stations. They would distribute power to substations located in the tunnel's service tube below the guideway. It's an elegant if ambitious plan. But what if something went wrong? Fire is one of the biggest concerns for tunnel engineers. The smoke from a tunnel fire has nowhere to go, making these fires unusually deadly. For this reason, massive fire suppression systems would be installed in every car. A collision would also be catastrophic. Because of the great distances involved, there would be no way to extract passengers or wreckage. And what if a tunnel train had to make a sudden emergency stop? Could a train behind it doing 5,000 miles an hour stop in time to avoid a devastating impact? To prevent disasters, the tunnel would need to be continuously watched, monitored by a network of sensors. The network would instantly register any failure, large or small, anywhere in the tunnel. Computers would immediately switch to disaster mode and execute automated procedures to minimize the damage. But there is one scenario that even the best safety systems could not prevent. It's a scenario that, if it ever came to pass, could render the Transatlantic Tunnel a severed, lifeless artery. The year is 2099. On a busy Friday afternoon at the tunnel's New York terminal, the 5:30 train for London is just departing. 1,000 passengers on board are settling in for the short, smooth ride. But 800 miles out at sea, disaster awaits them. An aging nuclear sub has just lost navigational power. All steering control is gone. As the crew fights to fix the problem, one system after another begins to fail. The captain suddenly finds himself not only without rudder, but without visual and without sonar. The sub is blind and now completely out of control. And it's heading straight for the Transatlantic Tunnel. The vessel weighs 50,000 tons, and it's armed with 16 nuclear warheads. A collision could be catastrophic. But as the sub comes within 2 miles of the tunnel, electronic motion detectors pick it up, triggering alarms at central control. Instantly, tethers closest to the vulnerable zone automatically slacken to allow the tunnel to sway upon impact. Too much sway is also a problem. If the tunnel is pushed too far out of position, the maglev guideway could warp, causing a disastrous 5,000 mile/hour derailment. The train and its passengers would be instantly vaporized. Back on the sub, the crew finally restores emergency power. It's too late. Just 200 feet now from the tunnel, the captain throws the engines into full reverse, while the crew braces for impact. The tunnel shakes violently, but it holds. The concrete and steel walls absorb the blow with only minor surface cracks. Incredibly, the passengers inside don't even feel a bump. At 5,000 miles an hour, they'd be miles past the point of impact in less than a second. And in a few days, a crew of divers will be out here to repair the surface damage. Yes, it is a happy ending. Of course, no one can know for sure unless the tunnel is built. A transatlantic tunnel. Nothing on Earth would even begin to approach its massive scale. Everything from the Great Pyramids to the Great Wall of China would be dwarfed in comparison. Yet despite its staggering cost and technical challenges, visionaries like Frank Davidson believe that one day it might happen.
Although a very difficult problem, the project is not at all as hazardous as flying to the moon.
If this tunnel were actually built, it would be one of the engineering wonders of the world. And as an engineer, I'd be very anxious to try it out.
What we forget is how far we've already come. The things we take for granted today were considered unimaginable yesterday. It seems to be our collective destiny to turn today's impossibilities into tomorrow's realities.